Yeah, it's my great pleasure for this, and I'm sorry for take so long time. Today I'll talk about some global effects of particle scalar curvature. Actually, this is a kind of survey of my recent journal work with my students and postdocs. There are two parts in my talk. The first one, I will focus on compact manifold with boundary. Is that okay?
Yes.
Yeah, okay.
Yes.
In this part,
yes.
I will assume a compact manifold with boundary admit a non-negative scalar curvature. Here, N and C refers to non-negative scalar curvature metric. For those manifold, the boundary geometry has deep relation with that of interior part, and actually, such problems have deeply related with positivity of quasi-local mass. I have to say that when I finished the slides of this part, I found that I have told this kind of talk had been delivered in this seminar last year. So maybe many people had already known that. I'm really sorry for that. And the second part, I will focus on Llarull type theorems on completely manifold. Now, the point behind here is that people intended to believe that one cannot increase the scalar curvature and enlarge the manifold in all directions simultaneously. Okay, this is on my talk. Now, let's get started from some basic facts of scalar curvature. So, by definition, the scalar curvature is trace of rigid tensor, and actually it is the most simple curvature invariant for Riemann manifold, with dimension greater than 3. A nice way to understand this scalar curvature is to look at the volume of smooth geodesic ball, which is denoted by BRP. Now, this is the formula. That is, volume of BRP is equal to omega n Rn to some factors. Now here, capital RP refers to scalar curvature at its P. So by this formula, we know that the larger the scalar curvature is, the smaller the volume will be. And for a manifold whose dimension is at least 3, we know that all such manifolds admit a negative scalar curvature metric, while not all manifolds admit a positive scalar curvature metrics. Actually, this is due to a classical result due to Rishinovich. So I think he proved this in about 60 years ago. Since then, what kind of manifold admit or cannot admit positive scalar curvature become one of central problem in Riemann geometry or topologies. Is it okay? So I will go on. Okay.
Yes, we'll switch.
To me, it is interesting to see the scalar curvature can be explained as energy density in general relativity. Here, GR refers to general relativity. So geometry of scalar curvature problem usually have deep relation with energy problem in general relativities. Now, one of basic problem in this direction is which is proposed by Professor Gromov, I think about 5 years ago. We call it filling problems. Now, let this sigma gamma H be a triples, which consists of sigma refers to differential manifold, closed manifold, and gamma is a Riemann metric on sigma, and the H, capital H, is a smooth functions, which will be served as mean curvature later. Now the problem is to find a condition so that this triple, which is called binding data, would or wouldn't allow the fillings of compact Riemann manifold denoted by omega g, so that H is a mean curvature of sigma in omega n with the outward unit normal vectors. And the boundary date of omega g is sigma gamma. Here, sigma is given different closed manifold, and gamma is given Riemann metric, and the scalar curvature is at least sigma. Here, sigma is the lower bound of scalar curvatures. 1 year later, Gromov posed formally more explicit problems. That is, let X be a compact Riemann manifold with scalar curvature bigger or equal than sigma. Then he conjectures that the total mean curvature boundary has a fixed upper bound, and this upper bound depends only on sigma and intrinsic Riemann geometry of Y. So I just say the problem is also interesting even if ambient manifold omega is given. Okay, now let me tell you that scalar curvature are actually involved on second derivative of matrix, while mean curvature are only on first derivative of matrix. So it is quite natural to use mean curvature as a boundary conditions. Okay. Now, so actually, Gromov, I think proposed more general field problems, I think in 1996. Now, here is a statement. Let Vg be a closed Riemann manifold, and S is a quadratic forms, which will be solved the second derivative later for the field W. And then pick up a curvature, maybe section curvature, Lich curvature, or scalar curvature, etc. And for each field in W, we can take infimum of K on W, and then we get a quantity which on W, which is a fielding, and then maximize it, and get a quantity only depends on VGS. So this is invariant of VGS. Now the problem is to try to evaluate or estimate these quantities. And this is the first part of the problem. The second part of the problem is try to understand the geometry of extremal or nearly extremal of fielding W. Okay. Now, such kind of problem, I would say that such kind of problems have deep relation with positivity of quasi-local mass. Now, let me give you very brief description of quasi-local mass. Roughly speaking, quasi-local mass is kind of geometric quantity of the boundary, which is denoted by sigma. It measures how much mass or how much energy contained the domain enclosed by sigma. And usually, quasi-local mass depends only on geometry of sigma, like mean curvature, area, etc. Now, let me show you some examples. The first example, so-called Brown-York mass. Now, here omega G is a compact, three-dimensional compact Riemann manifold, and the sigma is boundaries. And we always assume the Gaussian curvature of the boundary is positive. So by classical result due to Nirenberg, sigma, the boundary, can be isometric embedded into Euclidean space, R3. And the imagery also denoted by sigma. And H naught denotes the mean curvature or imagery in R3s. Now we have two images. The first one is H, and the second one is H naught, which is a mean curvature or embedded images. Okay, now Brown-York mass is defined by integral of difference of two mean curvature, that is H naught minus H. Because of the embedding, such kind of isometric embedding is unique. So the integral of H naught depends only on the boundary of on sigma. And if you deformed metric G and with the fixed induced metric on sigmas, and then you would see that the larger the mean curvature is, the smaller the Brown-York mass would be. Okay, this is for Brown-York mass. And then the second example is Hawking mass. This is a formula for Hawking mass. Here we have integral of H squared Wormhole functionals. And we also see that if the boundary, the geometric boundary is fixed, so the area of sigma is fixed, And then the largest mean curvature is, and the smallest of Cauchy manifold B. Now here is some common feature for quasi-local mass. First, it is a geometric quantity on the boundary domain. And the second, it is according to certain physical laws, the quasi-local mass should be non-negatives or has lower bounded. If the energy density, that is scalar curvature, is non-negative or has lower boundedness. And the third common feature for quasi-local mass is that the larger the mean curvature is, the less the quasi-local mass will be. So according to the second and the third one, we know that at least intuitively, there should be some restriction on mean curvature of the boundaries of sigma for all the negative scalar curvature fusion. At least such kind of mean curvature cannot be too large. Otherwise, we would have negative quasi-local mass while energy density is non-negative. So this is a contradiction to kind of physics law. Okay. Now, to investigate such kind of problems more further, we face the following problem. That is, let X be a compact manifold with an empty boundary Y, and gamma be any Riemann metric on Y. So the question is, can we extend the gamma into the interior part? Can we extend gamma to a Riemann metric which defined on the interior part, so that which denoted by G, so that the scalar curvature of G is positive? So this is a basic question raised by Gromov. About 2 years ago, my former students Wang Wang and postdoc Gordon Wei and me give a affirmative answer to this question. That is, for any compact manifold with an empty boundary X, Y, and gamma be any Riemann metric on Y, we can always transfer such kind of gamma to a Riemann metric G on interior part and with positive scalar curvatures. Okay. And after that, Professor Gromov raised some further questions for this. Now I would, this is some of them, 2 of them, but I will skip it. Actually, Professor Gromov himself has very nice, beautiful result on such kind of extensions. That let X be compact manifold with an empty boundary, and his theorem said that if the boundary is not empty, then there always there's a metric G on X with positive section curvatures. Now, in this case, there's no boundary restrictions. So how about rigid curvature? My former students Wenlong Wang and Jing Tianzhu told me that they had proved such a similar extension theorems like scalar curvatures. Okay. Now, they are a very beautiful application for our extension theorem, which due to Peng-Zhi-Miao. His result said that let sigma be a boundary on some compact manifold, which is denoted by omega. And given any Riemann metric on sigma, there always exists a constant H naught, depends only on gamma, so that if mean curvature is big than this H naught, there does not limit non-negative scalar curvature fusions. Okay, now the following pictures illustrate the main idea of the proofs. Now let omega be a given manifold with a boundary sigma, and gamma is a Riemann metric on sigma. And we just take the connected sum with a torus, n-dimensional torus. So we get a new metric. So we get a new manifold denoted by omega bar, let's say. And then according to the extension theorem, our extension theorems, the gamma on the boundary can always be extended to the Riemann metric, which denoted by G tilde, and with positive scalar curvature. And then we have mean curvature of sigma with respect to metric G tilde. And we define the H naught be maximums of absolute value h1 plus 1. And we claim that the mean curvature, if mean curvature h bigger than this h naught, there would be no natural scalar curvature field in for sigma, gamma, and h. Suppose not. We have a metric. We have the negative scalar curvature field in for such a boundary data. And then we just glue in those two manifolds together, and we get a closed manifold. And the metric is Lipschitz around the sigma, while it is smooth elsewhere, and the scalar curvature is positive. And note that the mean curvature is bigger than h naught, so we can always smooth it this mean curvature to get a Riemann metric, smooth Riemann metric with positive scalar curvature. While it contradiction to the Shenyang's result, that his result says that any compact manifold M connected some with a torus admits no positive scalar curvatures. Okay. So now, in order to investigate the Gromov theorems more closely, we need to the following quantities. Now, this lambda plus. Lambda plus is actually a supremum of total mean curvature among all the negative scalar curvature fusion of this triple. And here we need to assume h, the mean curvature h, which is mean curvature of the boundary with respect to orthonormal vector is always positive. Actually, for surface case, this quantity was introduced by Mantelidis and Ponchemel about 6 years ago, and they use it to study general Breuer mass. And we just to generalize this in higher dimension case. Now, we also get the following result, which is due to John work with Wang Longwang, Guo Dongwei, and Jing Tianzhu about. We said that now let MK PSC, now let boundary be the topological sphere, and we let MK PSC denote a smooth CK smooth positive scalar curvature metric, and so that the standard standard metric of the unit sphere is in this set. Let gamma be a smooth metric in this set, so that gamma is the scalar curvature gamma is positive, and we assume that gamma has always has isotopic to standard sphere metric. That is, there is a connected, that is smooth path in this set joins gamma with standard sphere unit metric. Under such conditions, we can show that lambda plus is always less than h naught. Here, h naught depends only on gammas. Now, here's a remark. If n equal to 4, that for S3s, all positive scalar curvature metric has connected path to standard sphere metric in this set. So that means this condition is automatically true. Okay. Now, this is for compact manifold with boundary case. Now, let's move to complete manifold. Now, in this part, I will talk about the Llarull type theorems. As I said before, that the main observation under this is you cannot increase mean curvature and enlarge the manifold in all directions simultaneously. Now, let me show you the simple examples. That is two-dimensional, let S2, G naught be a standard unit sphere. And suppose we have matrix G on this S2, and G is at least bigger than G naught, and scalar curvature of RG is at least 2. Then G must equal to G naught. Actually, this is a simple direction of Gauss-Bonnet formulas. Okay. Now, in order to investigate the Llarull type phenomenon more closely, Professor Gromov introduced the following notion, so-called epsilon gap length streamer. Now, Y is a closed manifold. G naught is a Riemann metric on Y. we said that G0 is epsilon length extremal. If there's no metric G bigger or equal than G0 on Y, and the scalar curvature of G is at least epsilon bigger than that of G0. And G0 was gap length extremal if for all positive epsilons. Professor Gromov also asked the following questions. That is, does gap extremity is always stable under Riemannian production with a Euclidean space? Now let's see the following examples. That is, this is n-dimensional unit sphere, and now G0 be a standard metric, and if G is another metric on this sphere with G at least G0, and the scalar curvature of G is also bigger than that of G0, then it must be G must isometric to G0. This is the Llarull type theorem, Llarull theorems, which proved, I think, 25 years ago. Now here's the remark. Under the assumption of under the Llarull theorems, under condition of Llarull theorems, the identity is actually one richest with degree 1. And actually, here the standard sphere can be replaced by any strictly convex type surface in Euclidean space. And the third remark is that Llarull type theorems was proved by using Dirac operators. And the first one is that one richest condition can be relaxed to area non-increases. So according to Professor Gromov's notions, we can say that the standard unit sphere metric, standard sphere unit sphere is actually delta gap length extremal for all non-negative deltas. Okay, any questions? Okay, as I said before, that the Llarull theorem original Llarull theorem was proved by Dirac operators. So it is interesting to see if we can prove it by mu bubble, minimal surface argument. Actually, now to my joint work with Yuhao Hu and my former student Liu Peng. Now our theorem said that this is a standard sphere with a pair of antipodal points removed, and the G hat is a standard metric. Let H be a smooth function at least bigger than 1 on this S3. Suppose that G is another Riemannian metric on S3 with antipodal points removed, and G satisfied bigger than H4 to the power of H to the power of 4 times G hat, and the scalar curvature of G is bigger than equal to H to the power minus 2 times that of standard spheres. Then H must be equal to 1. That is, G must isometric to standard metric G hat. Now, here's the remark. The theorem should be true if G is bigger or equal than H squared times G hat, and the scalar curvature bigger than H to the power minus 2 times standard and R G hat, which is a scalar curvature of standard unit sphere, and H is at least bigger than 1. A special case is the Llarull theorem on 3-dimensional case. Now, the third remark is that the assumption that H is bigger than 1 cannot be important in our theorems. It cannot be removed. Otherwise, we will have counterexample, as I state right here. The last remark is that we do not know whether the result is true or not if O and O prime are not antipodals. We use the mu bubble argument to prove this theorem 1. Now, the point behind the proof is that actually the standard 3 sphere can be regarded as a foliation of a family of mu bubble. And each mu bubble is actually a geodesic sphere with center at the north pole. So we want to use this to to show such mu bubble also exists in the new metric. To do this, we first need to show the existence of initial mu bubble for certain mu by perturbation arguments. Now, secondly, we have to show this mu bubble has connected components which denote by sigma naught, and whose projection onto equator S2 has non-zero degree. I draw the picture here. Now, the third step is to construct a foliation start from this mu bubble, sigma naught, and to show the induced metric on each leaf is a foliation agree with that from G hat. Now, then the first step is to show the section curvature of domains swept by this foliation is ones. And the last part is to show the Hall manifold can be swept by these foliations. Okay. Now here is a definition for mu bubbles. Actually, mu bubble is a boundary of minimizer for the following function, which is called brain actions. And here omega is Cassipoli set on the manifold. Now, here's the basic facts for mu bubble is that the mean curvature of mu bubble is mu, I mean with respect to outward uninormal vectors. Suppose, here's example for mu bubbles on standard spheres. All geodesic sphere in S3 with center north pole are kind of mu bubble with mu equal to 2 to the cotangent rho. Here rho is distance to north poles. Okay. Now this is for three-dimensional. The advantage for three-dimensional case is that mu bubble is two-dimensional. So Gauss-Bonnet formula plays a crucial role. That means depends Gauss-Bonnet formula heavily. So how about high dimension case? Now we will consider the model space like this. Here is a standard sphere SK times n, a manifold capital N. Here n being enlargeable. For instance, n may be equal to n could be a torus or n could be Euclid space. Now here's the natural problems. Let Ng be compatible Riemannian manifold with scalar curvature bigger equals than this k times k minus 1. And we assume that there is non-zero degree and one Lipschitz map from map to the model space. Here our model space is Sk times n minus k dimension torus. Now the question is Mg is locally isometric to our model space? Now this is the first problem, and which is a model space is compact. Now this is the second problem. We have several problems. Let Mg be complete ornithal Riemannian manifold with scalar curvature bigger equals than this constant, and we assume the non-zero degree one Lipschitz map from this M to our model space. I think it should be the map should be assumed proper. So the question is Mg locally isometric to the model space? So this is kind of the Llarull type theorems for complete non-compact case. Yeah, are there any questions? Actually, I will give answer to those two questions later in my main part of talk. Now, here's the remark. If the answer to above problems are affirmative, there would be no such map provided scalar curvature is strictly bigger than this constant. Actually, this constant is a scalar curvature of model space. Now, actually, there are three type of model space. First one is F. There is FQSM. A scalar curvature is bigger than equal to n times n minus 1. The second one is MQSN minus 1. N minus 1 dimensions standard sphere times R. R is lines. The scalar curvature is bigger than Z. And the last one is that is MN to SK times R minus M minus K dimensional Euclidean space. Here, M minus K is always bigger than Q, and the scalar curvature is than that part. Now, here are some relevant results on this. Now, let MG be a compact manifold, and we assume the second homotopy group is non-zero, then we can define a kind of sisters like this. That is the increment of the area. Here, sigma is non-contractible immersed sphere in M's. We call it sisters, maybe. So, and then here's the theorem due to Hilbert, Simon-Brando, and Nevis. They proved that for three-dimensional manifold MG, scalar curvature is bigger than 2, then this quantity is always less than 4 pi. And equality holds if and only if mg bar is locally isometric to S2 cross R. This is for three-dimensional case. Later, Jing and Zhu generalized their result to high-dimensional case. Now, this is a high-dimensional case. M is M plus 2 dimensional manifold. G bar is a Riemann metric on this, and the scalar curvature is still bigger than 2. And also, this manifold admits a non-zero degree continuous map. M to the model space is S2 times Tn. Tn refers to n-dimensional torus. And then he showed that this A is less than 4 pi. And equality holds if and only if it is locally isometric to S2 cross the Rn, the n-dimensional Euclidean space. Now, basically, those things are two-dimensional problems, so they still need Gauss-Bonnet formulas. 3 years ago, Wei Ping Zhang proved the following result, and let MG be non-compact manifold, non-compact and complete spin manifold. And F is mapped from M to Sn, and F is constant outside a compact set. And so we can do it. Because F is constant at infinities, then we can define the degree of map. And he assumed the degree is non-equal to 0 and the area non-increasing. So scalar curvature is bigger than that of unit spheres on the support set. And then he can show that increment scalar curvature is negatives. As corollary, we have the following result. Let MG be non-compact and complete spin manifold with scalar curvature big sense, strictly big sense that constant. Then there is no continuous map from M to Sn, so that it is constant outside a compact set and degree non-zero and the area is non-increasing. This is just a corollary. But in those results, we need to assume the manifold is spin because they use Dirac object argument. Now, the problem is that, is it possible to show the same result without spin assumptions? Actually, this is conjecture D is due to Gromov. He wants to show the Llarull type theorems for on Sn minus a point. And if the metric G is complete, then the result is true. But we still don't know if there are no G, it may not be complete. Now, the difficulty, one obvious difficulty is that for high dimensional case, the manifold may not be spin. So Dirac operator cannot be used directly, and Gauss-Bonnet cannot be used on its movable either. Recently, we have result. This is joint work with my student, current PhD student, Tianzhe Hao and Yuguang Shi, with my postdoc. We proved the following result. Let MG be n-dimensional compact analytical manifold with scalar curvature bigger than 6, and the dimension n is between 4 and 7. We assume that there's non-zero degree and one repeats map from M to model space. Here, model space is S3 times n minus 3 dimensional torus. Then we can show that such a M is always locally isometric to its model space. Okay. Now, here's the problems. Let MG be a non-compact orientable complete Riemann manifold, and the scalar curvature is bigger than 6, is bigger or equal than 6, and F is from M to the model space, be a plot and one ellipse map with a non-zero degree. Is it possible to assure that MG is locally isometric to the model space? That means the Llarull type theorem is also true. Is the Llarull type theorem true on this case? I should say that non-compact situations are much more complicated than those of compact case. Now, here's a simple observation. That is, Llarull type theorem are not true on Euclidean space for n bigger or equal than to 2. Now, here is an example. Let sigma n be a paraboloid of revolution in n plus 1 Euclidean space. So it is sigma n is a graph of Rn. And let P be projections, standard projection to Rn. And it's easy to see that this projection is actually is one Lipschitz and progress, while the scalar curvature or paraboloid revolution is positive. So the Llarull type theorem is not true in this case. Now, by modifying a little bit, we can get following examples. Now, let sigma n be a paraboloid of revolution in Euclidean space, and P denotes the projections. Let MG be the Riemannian product of sigma n with m-dimensional sphere, and we assume m is bigger than 2. And then scalar curvature is of the G of this product metric is strictly bigger than that of m-dimensional unit sphere. And this F, which is the first component, is identity map. And the second part is projections. Is a proper and one Lipschitz map with non-zero degrees. So that means the Llarull type theorem is also not true. And this example illustrates that the times Rm stabilized mapping theorems in the Professor Gromov cannot be pointwise. We only have these ones. Okay. Any questions? Okay. Now, here's an observation. So there's no proper one Lipschitz map from Euclidean space to I'm sorry that here G is a Riemann metric on n-dimensional Euclidean space, and the scalar curvature bigger than deltas. We call it uniform positive scalar curvature, and then we can show that there's no proper and one Lipschitz map from this RNG to standard unit sphere Euclidean space. Now, by the similar argument, together with our theorem 1, that is the Llarull type theorem for compact case, we get the following result. That is, for any delta is positive, let MG be a Riemann manifold. Here we assume n should dimension is between 5 and 7. Be a non-compact and orientable complete Riemann manifold with scalar curvature is strictly bigger or equal than 6 plus delta. Delta is any positive constant. Then we can show that there's no proper and one Lipschitz map from this n to model space with non-zero degrees. Okay. Now, our third observation is that any compact perturbation of Euclidean space with non-negative scalar curvature is trivial. Actually, this observation is a special case of positive mass theorems. And by similar argument, together with our theorem 1s, we get the following theorems. That is, for any for this for remaining manifold MG and dimension between 3 and 7. We assume this remaining manifold is non-compact, orientable, and completely ones. With scalar curvature is at least 6. And F is from M to this model space via plot and boundary-piece map with non-zero degree. Then MG is isometric to model space if F is isometric outside a compact is isometric outside the compact domain of M's. That is, if we use compact perturbation on this model space with scalar curvature bigger or equal than 6, then this perturbation must be trivial, just like positive mass theorems. So just like Euclid space case. Okay. Now I should finally I'll tell you that saturation is completely different if we use S3 cross R times R as a model space. Now we can show that if this MG is a 4-dimensional non-compact orientable and complete remaining manifold, the scalar curvature is bigger or equal than 6, and F is mapped from M to a model space via plot and one piece map with non-zero degree. Then, if MG is geometrically bounded, that is the supremum of scalar curvature. The supremum of curvature operate is bounded, and injection radius has a lower bounded. Then, MG must isometric to this model space. This is our rigid theorems. We believe that the geometric bounded assumption is not necessary, but for time being, we don't know how to remove it. Okay, any questions? Now, the last theorem is that this 4-dimensional is non-compact orientable complete manifold with scalar curvature strictly bigger than 6. Now the scalar curvature, now in this case, the scalar curvature is strictly bigger than 6. Then there is no plot and one piece map from this model space to from M to the model space with non-zero degrees. Okay, now combine all those things together. What we prove is the following ones: that is give a partial answer to question D due to Professor Gromov. That is, for any positive delta, and the delta gap length extremity of the 3-dimensional sphere is stable under times of under remaining products of Euclid space. Okay, this is what we did. What are we doing now? I think I should stop here. Thank you for your patience. I'm really sorry for occupying too much of your time at the beginning.